Okay. All right. So we'll begin, and we are continuing on. We are talking about importance sampling. I've got a couple examples here, and we'll take a look. All right. So before we get into importance sampling, just regular old Monte Carlo integration looks like this. That means we want to find the expected value of this function h applied to a random variable x, where x is generated by this PDF f. And if that's what it looks like, then it's equivalent to having the integral of h of x multiplied by f of x dx. And we can estimate that by drawing a bunch of x's from f. We apply h to all of those x values, and we take the sample mean here. Okay, and so here we have h bar sub n. That's our Monte Carlo estimator, and in order to do this, we need to be able to produce random samples from f of x. Okay, and today's kind of lesson is, what do we do if we cannot produce samples directly from f of x? All right, is there something that that would work? Okay, so so here we have we have a couple alternatives, right? And one is to learn how to generate random values for different distributions, and this is what we're going to do next week. We're going to focus largely on that. Or today we can look at performing importance sampling, and R is able to generate a whole bunch of values from all of these distributions, the uniform, normal, beta, and all of this stuff. But we'll talk about doing importance sampling. Now, the examples I've done today will feel a little contrived because we're already kind of, for I think all of my examples, we are able to generate values from that distribution directly. But this will apply for any kind of situation where you want to calculate the expected value of some kind of function, and it's difficult for you to generate values directly from some distribution. Okay, and so this is what we want. This is what we want to estimate, but in our situation, we can't generate values from f. We have to generate values, and we're going to generate values from an entirely different distribution g. Okay, and the only requirement here is that the support of f has to be contained within the support of g. Okay, we don't want any situations where f is not 0, but g happens to be 0. Okay, so so the requirement here is that g has to be greater than 0 anywhere f is greater than 0. Okay, you can have the opposite situation. It's okay for f to be 0 and g not to be 0. That's okay, but in this situation, we need to make sure that g is going to at least generate some values wherever f would have generated values. Okay, because what we're doing is we're going to generate values from g, and we don't want a situation where f would generate a value like 6, but g would not generate a value like 6, because that would be a problem. Okay. And so mathematically, this is what happens, is that we say the expected value of the function h applied to the random variable x, where x comes from the PDF f, is equal to this integral. The integral over the support of x, or basically the support of f, where it's h of x multiplied by f of x dx. Okay. And effectively what I'm doing is I'm going to multiply this by g of x over g of x. Okay. And I just kind of rearrange terms. Okay. So now I have h of x times f of x divided by g of x multiplied by g of x. And so here I can create a bracket And now this is kind of in the form of a function multiplied by a density. Okay, g of x is a density, and this is the function. Okay, so over here I've got the expected value of h of x, where x comes from f, is basically the function h of x multiplied by the density f of x. And here it's in the same form. It's just a complicated function multiplied by a density. All right, so it's just, this is the function multiplied by a density. And so this can be expressed in this expectation. Okay, it's the expectation of now this mess of a function, h of x times f of x over g of x, where x is a random variable generated by g. Okay, so all we're doing is we're kind of just rearranging terms so that we get the integral of a function multiplied by a density, probability density. In this case, our function is h of x, f of x over g of x, and our density is g of x. All right. Okay, is that all right? Does that feel okay? All right, let me go ahead and give you your first viewing quiz answer for today. First viewing quiz answer is B as in bear. Okay, B as in bear is your first viewing quiz answer. All right, and so the steps are basically the same as before. This time, so if you think of how Monte Carlo integration works, you generated values from f, but this time we're going to generate x from g, and then we calculate the value of the function, h of x times f of x over g of x, okay? So we just calculate h of x times f of x over g of x for x1, for x2, all the way up through xn. And then we're going to estimate this by taking the mean of all of those h of x times f of x over g of x. Okay, and that's it. All right, so I wanted to try to provide, I don't know, like, sure, it looks fine like this, but if you sit and think about it, it's a little bit crazy, or to me it feels a little crazy or mind-blowing, that we can estimate the value of a function as if it were applied to a different random variable, even though I'm only able to generate values from a different distribution, right? So for example, you know, so the idea is, you know, again, we want, we're going to draw values from g, okay? But we want to estimate the expected value of a function as if the values x were drawn from f, right? So how's this going to work? I'm drawing values from g, but I want to estimate the function as if the values were coming from f, right? And the reason why it works is that the values that we draw from g are going to get weighted by this thing, f of x over g of x, right? So let's say f is a beta 2,4 distribution and g is a beta 5,3 distribution. So these are both beta distributions, so they have the same support. That is, they go, both will generate values from 0 to 1, but f and g have very different shapes, okay? And at least for the purpose of this example, we're going to pretend that our computer can generate values from g, but it can't generate from f, okay? So yeah, it's a bit of a silly, contrived situation, but we're gonna try to estimate a function as if the values came from f, but not from, came from f, even though the values are actually coming from g, okay? And just to give you a comparison, f is in blue and g is in red, okay? So if you look at f, which is in blue, you know, if you had to kind of eyeball where the mean is, where would you say the mean of f, the blue distribution, is? Just any guesses here?
Probably like 0.35.
Yeah, something around there, right? Okay, so the mean is somewhere around here, 0.3, 0.35, something around there. Okay, whereas what we're generating from is g. We're generating from the red distribution, and that looks to have a mean around 0.6 something, 0.7, something around there, right? Okay, so how is this going to work? We're generating values from the red distribution, but we want to pretend as if the values were coming from the blue distribution. And you know, so what do we do? Okay, so if beta is a 2-4 distribution, the mean of f, this should say mean of g, mean of f is going to be 0.333, and if g is a beta 5-3 distribution, the mean of g is going to be 0.625. Okay, and that's kind of reflected in these two pictures here. So the mean of the blue distribution is 0.333. The mean of the red distribution is 0.625, right? And again, we're going to pretend like we didn't know these. Like this is the analytical answer. Let's say we don't know the mean of f and we want to estimate the expected value of f via Monte Carlo, right? So, you know, if we were able to sample from f directly, it's easy. All we do is we just generate a whole bunch of values from f and then we take the mean, right? But what we're stuck with is that we have to generate values from g, okay? And so if I generate a bunch of values x from g and then take the mean, you know, my Monte Carlo estimate is going to produce a value that's close to 0.625, which is the mean of the beta 5-3 distribution, right? So this should come as no surprise. Here I'm going to generate 100,000 values from a beta distribution with parameters 5 and 3. And if I take the mean of all of those values, I'm going to get 0.625. Okay, so my x has been generated from g, but I want to be able to somehow use these x values. I want to somehow use these values to estimate the mean of f, which is an entirely different distribution. Okay, so can't, even though my x has come from the g distribution, what can I do something to these x values to get the mean of the f distribution, right? So my values came from the red distribution. Can I somehow estimate the mean of the blue distribution? Okay, and the answer is we're going to take each value that we've generated and we're going to weigh them by this quantity, the importance weight, right? And so, you know, if we look back here, the part of the issue is that when I generate values from the red distribution, I'm going to generate values like 0.7 way too much. Okay, 0.7 is going to show up way too often in my random sample. Okay, whereas values like 0.3 or 0.2 are going to show up very, very infrequently. Okay, they do show up. They do show up a little bit in my sample of x values that are drawn from G, but you know, the blue distribution F generates 0.2 way more often than the red distribution does. Okay, so I'm going to take each of these values and I'm going to kind of weight them appropriately, right? So when my red distribution, when G produces a value like 0.7, okay, so when G produces a value that's close to 0.7, I'm gonna take those values and I'm gonna just weigh them less, okay? So compared to F, G produces 0.7 like way too often, so I reduce their weight, okay? And if you look at the density of G is much greater than the density of F, so this weight, F divided by G, is gonna be less than 1. Here we got a question. It says, do we need a larger sample size than normal when doing importance sampling? So I guess it depends like how accurate you want to be. So if you want to be equally accurate, then if you were able to generate from the distribution directly, yes, you would need a larger sample size. But your sample size, there's not like a straight answer for everything. It depends how similar F and G are. So F and G are very similar. You don't need that much of a bigger sample size. But if F and G are drastically different, because this is going to work for any two PDFs F and G that share the same support, or at least where G's F is, the support of F is contained within the support of G. This will work. But if F and G are, drastically different, then you don't need as large of a sample. Okay. And in some cases, importance sampling is going to reduce the number of samples that you need in terms of if you can kind of rearrange the original idea here. But anyway, I'll get to that. Okay, so and then on the other hand, if my sample produces, when I'm drawing values from G, okay, and it produces a value that's close to 0.2, I have to weigh those a lot more heavily, right? So if I look at kind of my plot here, all right, how often does G produce a value like 0.2? Okay, sometimes, not very often, but sometimes it produces a value like 0.2. So when I get one of these values, when I look at the blue distribution, I know that the blue distribution F, puts a lot of weight on 0.2, right? It's producing a lot of these values. So I'm going to, so when G does produce a value near 0.2, I have to make it quote unquote count, okay? And so the value of G, or the value of this weight, is going to be greater than 1 because G of 0.2, the density at 0.2 is much less than the density at F, okay? And so the weight is going to be greater than 1. So wherever F is greater than G, I have to weigh those values more, and wherever G is greater than F, I weigh those values less, okay? Because we're generating values from G, and we kind of want to weigh them accordingly so that the calculations will get so that the calculations will balance out. Okay. So this is what we've got. All right, and so these weights can just be calculated by taking the ratio between the densities. Okay, so I can take the exact same sample from earlier, and all I have to do is I just multiply each of these values x by their weight. Okay, and I can estimate this by taking the mean of x multiplied by the weights. Okay, so the weights are just going to be the density of the beta 2,4 distribution divided by the density of the beta 5,3 distribution, because F is the density of the beta 2,4 and G is the density of the beta 5,3. And so here I take my weights W, all right, and then I just take X and I multiply it by W, and when I calculate the mean, I get something a lot closer to the true mean. Okay, so the true mean is 0.333 1/3. Okay, and my X values came from the beta 5,3 distribution, which is going to have a mean of 0.625. And using those exact same values, I didn't like resample X or anything. If I just modify X by multiplying by their weight, the mean ends up being 0.333 or something very close to the true mean. Okay, and I think this is kind of an impressive result that that we're drawing values from a completely different sample and still we're able to kind of get the quantity that we want. Okay, and just to kind of show you that it's not a trick, if I create a histogram of X, we can see the histogram of X directly matches the beta 5,3 distribution. Okay, it comes from the wrong distribution, the red one. But again, when I weigh them, okay, then I can calculate the mean of the blue distribution. Right. All right, and I got a question in the chat. It says, can you choose any distribution as the proposal, but some converge faster than the others? Okay, so the answer is yes, you can. This proposal distribution G of X, whatever we're using here, it can be any distribution as long as it meets this requirement. The only requirement is that the support of F has to be within the support of G. Okay, so if your F is like the normal distribution, which has a support of negative infinity to positive infinity, okay, your G distribution, your proposal distribution also needs to go from negative infinity to positive infinity. You can't suddenly, you can't decide, oh, I only want, you know, these values or something like that, okay? So, so any, so in our case, you know, the beta 2.4 and beta 5.3, their support goes from 0 to 1. We could have used the uniform from 0 to 1. We could have used any distribution that contains the interval 0 to 1. So as long as you have that, meet that requirement that the support of F is contained inside the support of G, it'll work. And yes, some values are going to converge faster than others. Okay, so some proposal distributions will converge faster than others. Okay. Is that all right? Any questions on this? Does this feel all right? Does this seem like, I don't know. I think it's neat that I'm able to get this value, even though my sample came from the wrong distribution, okay? And it's all kind of controlled by this W, this weight, okay? And so, so the algorithm I had written earlier, it can just kind of be written this way, in that we generate the X values from G, and then we calculate the weights for everything, and then we're going to estimate this by multiplying H times the weights. Okay. All right. So we have a question. It says, I thought we were assuming that we can't use the density function for the beta function of 2.4. Why are we allowed to use it to calculate weights and not just sample from it directly? Okay. Okay. So yes, you do need to know the function, the density function. We're just saying so we know the density function, we're just not able to sample from it. Okay, so perhaps you have, so I know this example is a little bit silly, but it's a situation where you are able to, you know, the shape of the density function, but generating a random sample from a given density isn't always easy. Okay, so so we haven't worked with trying to generate random samples, but that's what we're going to do next. Okay, so so it's as if so we can calculate the density function d beta, but for whatever reason our r beta for 2.4 doesn't work for us or something. Okay, so we're able to calculate the density, but we can't generate values from it randomly. Okay, all right. An example, can I give a real world example of when this might be applied? So let's see. So you might want to estimate some kind of integral. Okay, so I have a homework assignment. I don't know, it's not really a real world example. It's just a contrived example where I want you to estimate the integral of some function. And you know, it's this weird function, and you're not able to generate values from that PDF directly, okay, because it takes on this weird shape. So what you're going to do is you're going to generate values from different distributions, either like the uniform or this, you know, like a normal distribution or something. And when you do that, you can get, you can estimate the thing. I've got a couple examples. They're not exactly real world examples, because all of these examples have kind of been solved by having the p norm function. Okay, the p norm function, which in R gives us kind of the cumulative normal density, is you know, this has only been available, well, it's been available for a while now, but you know, and in like the grand scope of things, it's more of a newer development, right? Being able to estimate the cumulative normal distribution, you know, with 16 decimal places of accuracy. That's you know, on a grand time scale of things, has been a more recent development. And so a lot of these examples I'm using are a little bit silly, but they work, right? Okay, so so this is an example. Again, this has already been solved because we are able to generate values from the normal distribution. We are able to do this, but the example here is the folded normal distribution, right? So the folded normal distribution is the distribution of values that you would get if you just took the absolute values of the normal distribution, right? So you have a standard normal distribution, which generates values from negative infinity to positive infinity. But if you take the absolute value of everything, you're only going to get, it's going to go from 0 to infinity. And in order to make sure that the PDF still integrates to 1, the PDF of the folded normal distribution is going to be twice as tall as the PDF of the regular normal distribution. So your PDF is going to be 2 times the PDF of the standard normal. So this is PDF of the standard normal, and our function is twice as tall as this. Okay, and so if I do this, I'm going to get this is the PDF that I have. Okay, and if the support of this function of the folded normal is going to be from 0 to infinity, and we can say, you know, what's the mean? What's the mean of this? Okay, and so in this case, you know, what's the expected value of x, where x is coming from this distribution, and in our case, you know, that function h of x that we want to estimate is going to be just x here. Okay, and so, you know, it's a contrived example or a contrived scenario, but we'll use importance sampling to do this. Okay. Oh, let me give you your second quiz answer. Second quiz answer is A as an apple. A as an apple. Second quiz answer. Okay. So again, it's a contrived scenario because technically we don't have to use importance sampling. Like, we can estimate it directly. I can just generate a million values from the normal distribution. I'm going to get z. I can take the absolute value of z, and I can say, what's the mean of that? Okay. And so if you only take positive values of the normal distribution, the mean ends up being something around 0.797. Okay, something around there. So this is a million values. We just take the absolute value, and we're going to take the mean of these things. Okay, but again, we're going to pretend like we can't generate from the normal distribution. And again, all of these examples are a little bit silly because we're going to say we can't generate from this thing, but we are able to generate from this other distribution. So in this case, we're going to generate values from the exponential distribution, right? So so the PDF of the exponential distribution, if you have a rate parameter of 2, is going to be, you know, the PDF is lambda e to the negative lambda x. So we're going to get g of x is 2 times e to the negative 2x. Okay, and the support of the exponential distribution is also 0 to positive infinity. Okay, so these two things have the same support. All right, so this will work. Okay, and we are able to sample from g of x using random exponential in R. Okay, and so, you know, again, I feel these examples feel a tiny bit silly just because the kind of the premise or the setup of importance sampling is that we're not able to generate from this distribution, but we are able to generate from this distribution. But all these examples I've been doing so far, like, technically we can generate from the normal distribution. Okay, but just go with it for now, please. All right, so so what we need to do is, so we've got the exponential density that we are able to generate from, and this is the density that we're going to pretend that we can't generate from, f of x. Okay, so so we're going to generate values from the exponential. Okay, and then the weights are going to be f divided by g. Okay, and so again, we know what the density function is we just don't know how to generate values from it, okay? So this density function up here is 2 times d norm, okay? And the density function on the bottom is going to be d exponential, okay? So we have the form of the densities, but we're going to pretend that we can't generate from f, okay? And right now we're pretending, but there will be some situations in real life where you truly might not be able to generate from f. Like you have an idea what the density looks like, but you're not able to generate from it. Okay, and again, you've got a couple examples in your homework, and we're gonna calculate these weights, which is found by we can use d norm and d exponential, and then we're gonna estimate this quantity. All right, and in our case, h of x is just x because we just want the expected value. And it's going to be basically the mean of the hx, which is just x in our case, multiplied by the weights. Oh yeah, sorry. This is a persistent typo because I keep copying and pasting stuff. It should say from j equals 1. J equals 1 to n. So that's a typo. All right. Okay, so here I'm going to generate a million values from the exponential distribution. So x is coming from our random exponential values. My weights are 2 times the normal density divided by the exponential density here. And the estimated mean is going to be mean of your x values multiplied by the weights. I just do x times w, and the mean of that is going to be 0.797. Okay. Earlier, when we generated values directly from the normal distribution z, and I took the absolute values and took the mean. Okay, so this is the Monte Carlo estimate where we're able to generate from f. I got 0.797, and then the theoretic value, if you do the calculus or whatever, I don't know how to do it actually. The theoretic value is the square root of 2 over pi, and that's also 0.7978. Okay, so we can see these are all quite close to each other. Okay, off by less than 1/1000th. Okay. All right. Okay, and so that's kind of the accuracy that you get when you generate a million values. You should be within about 1/1000th of the true value. Okay, is that all right? Okay. If you kind of plot this, the red line is the exponential density. The blue line is the density of the folded normal. Okay, and this black line is the weights that we apply to the values generated by the exponential distribution. Okay, and this is just I drew a horizontal line at 1, and so you can see when the exponential distribution produces from the red line, it produces way too many values between 0 and 0.5. Okay, it produces too many values between 0 and 0.5, but then not enough values that are greater than 0.5. Okay, and so compared to the folded normal, which is this blue line, whenever you get a value greater than, less than 0.5, we have to weight those values less than 1. Okay, and then as we go farther away, we have to weight these values a lot more. So the normal distribution says, values like 1 should be produced more frequently, and the exponential doesn't. So we have to weight these. All right, and it's just kind of interesting that kind of the ratio ends up following this large curve here. But you can see how the weights are less than 1 in locations where red is taller than blue, and then the weights are greater than 1 in the locations where blue is higher than red. All right, we're going to finish early today. I think that's okay. All right, so here's another example. What if we wanted to estimate the probability that a random z from the normal distribution is over 4.5, okay? So, what's the probability of getting z greater than 4.5? Okay, so that's going to be 1 minus p norm of 4.5, and that's on the order of 3.397 times 10 to the negative 6, okay? So about 3.4 times or 34 times and 10 million, okay? So this is a very small value, okay? I have already generated, back here, I generated a million values from the normal distribution. And so using regular old Monte Carlo integration, remember, we can just, we learned how to calculate the cumulative distribution function by just kind of doing the indicator function that's from a couple, I think last lecture. I could just say, well, all right, I have a million values. How many times was z greater than 4.5? Okay, and our answer is it happened 2 times in a million, right? So I generated a million values, it happened twice. And therefore my Monte Carlo estimate is 2 in a million, okay? This is not a very great estimate. The true answer is closer to 3.4, but just because this is such a rare event, even in a million attempts, it happened only twice, okay? And the true answer is that in a million attempts, it should happen between 3 and 4 times. The fact that it happened twice isn't that weird. And I could say, well, if I want to get a much more accurate estimate, maybe I could generate 10 million or 100 million random normal values, okay? And even with 100 million random values, who knows how accurate my estimate is going to be, okay? So, the problem is that if you think about what we're doing here, maybe I'll draw a picture. Okay, is that oh, that's terrible. All right, I don't know what okay, so this is a terrible normal distribution picture. My goodness, I'm struggling drawing. Okay. All right, so if this is 0, and again, by the time it, technically the normal distribution, by the time it gets to 4.5 is very close to 0, right? So we have 4.5, and we want to know what is in this, what's in this tail over here, which is technically very, very, very narrow, right? So this is such a terrible picture, but anyway. So we want to know what proportion is in this tail greater than 4.5, okay? And if you think about it, if f of x is basically the normal PDF, and we want to know what's the probability that x is greater than 4.5, basically what we're saying is that this is equal to the expected value of f of h of x, okay, where h of x is basically the indicator that x is greater than 4.5, right? So the indicator function, if we were to graph this, is basically 0 here, and then 1 over here, right? All right, so the indicator function of x greater than 4.5 looks like this, okay? So where this is 0 and 1, okay? Obviously not on the same scale as the density. Okay, so we want to know how often do we end up over here, and the problem is that when we generate values from the normal distribution, it produces like 99.999% of the values are less than 4.5. And, you know, in a million, we only got 2 hits that were greater than 4.5. So, so again, to improve our accuracy, we have to either sample many more values, or an attempt is we can use importance sampling. And so an alternative, instead of generating values from the normal distribution, is that okay, which instead of generating values from the normal distribution, which produces way too many values that are less than 4.5, I can just take an exponential distribution. All right. So if the exponential distribution is lambda e to the negative lambda x, and I can just take with lambda equal to 1, I can just get e to the negative x for with lambda equal to 1. And we can just start it x greater than 4.5. So we can just kind of shift the exponential distribution over to start at 4.5, and we can say just generate values from the exponential. So basically I'm just going to whatever exponential distribution I have, I'm just going to add 4.5 to it, right? So exponential generally generates from 0 to infinity, but I'm going to just add 4.5, and that basically just shifts everything down, right? Okay, so then what's the PDF? What's the PDF of this thing? Okay, well, basically I'm just shifting everything down 4.5. Okay, so so basically it's just e to the negative x minus 4.5, where I've just kind of shifted everything down. I did a little bit more math here. Basically, it's the exponential distribution, but I have to kind of shift it by a constant. And so so I can think of, well, if it's the exponential shifted by a constant, I can also, or you know, scale it up. I can just integrate from 4.5 to infinity, okay? And this becomes e to the negative 4.5, and I'm going to basically just get e to the negative x minus 4.5. Is this all right? So all I've done is so again, part of the problem with this is that when I generate from the regular old normal distribution, I generate way too many values that are less than 4.5. So I'm going to generate from the exponential distribution, and it's going to produce only values greater than 4.5 by shifting it down. Okay. And so, so the weights of this are going to be the PDF of the normal distribution, the regular old normal distribution, divided by the PDF of my shifted exponential distribution. Okay. And we just want the probability of being in the tail. Okay. I'm not looking for the mean or anything. So the probability of being in the tail is just this indicator function of, you know, is x greater than 4.5. So that's going to be 1 for everything where x is greater than 4.5, and 0 for everything where x is less than 4.5. Okay. And in our case, because we're only generating values that are greater than 4.5, basically my I is 1 for everything. So I don't have to worry about that. Okay. So here I just generated 100,000 values. Okay. I've got the exponential, I generate 100,000 random exponentials, and then I add 4.5 to everything. So I'm just kind of shifting everything down. Okay. And then I calculate the weights, which is going to be d norm of x, the normal density divided by the exponential density, where I subtract off, you know, 4.5 from these things. And then my h is basically 1. So I guess I could have w times 1, because all of my x's are greater than 4.5. So I get the, you know, what's the mean? And the mean is going to be 3.375, which is quite close to the true p norm value of, you know, 3.397. So So this is a lot more accurate. My estimate here is more accurate than just trying to generate values from the normal distribution and saying how often do we get values greater than 4.5. Okay, all right, so that is that's all I've got for you guys today. The last quiz answer is C as in cat. C as in cat. I've posted the your second homework assignment. It's available under week 3, and it will be due a week from Monday. So that gives you about 10 days to work on it, I think. So do a week from Monday. Your second homework assignment's available in week 3 on CCLE. All right, we'll end here for today. Have a good weekend, and we'll see you guys later.